Hello everybody, and thank you very much for being there. My name is Asunción Jiménez Cordero, and I'm going to present a joint work with Juan Miguel Morales and Salvador Pineda, the three of us belonging to the Oasis Research Group from the University of Malaga, and the title of my talk is Interpretable Learning in Power System Operations. So this is the outline of the presentation. So first I'm going to motivate you a little bit the problem, then I'm going to introduce you a little bit about the supervector machines. Then we formulate the optimization problem that we proposed, and we test its efficiency on an illustrative example, and finally we give some conclusions and future research lines. So in this talk, I'm going to work with the unit commitment problem, which is one of the most important optimization problems in power systems. It has some binary variables that model the on-off status of the generators, and therefore it becomes a mixed integer linear programming problem very hard to solve, especially for large systems. And therefore, recently it has been very popular, the study of the line congestion, in order to select which are to know which are the lines that are congested or not, to simplify the problem and therefore to make an easier resolution. But in this work, we don't only focused on these lines will be congested or not, but we also want to focus on the interpretability and want to know at which node do I have to focus to know if the line will be congested or not. So the aim of this presentation will be to design a mathematical optimization approach to select the most important features or the most important nodes, to classify, to identify the line congestion status. And because we are working with a real-life application, we want to take into account not only the information provided by the data, but also the information provided by the physics of the problem. So the line congestion identification problem can be reduced to a binary classification problem where we have some input data, which are the demand, and we want to find a classification rule that separates between the congested lines from the non-congested lines. And to deal with this binary classification problem, we are going to use the well-known machine learning technique, support vector machines, SVM. So SVM, the aim of SVM is assuming that we have a set of points, the blue ones and the red ones. For instance, we can imagine that these points correspond to certain demand values, and the blue points are the non-congested lines, and the red points the congested lines. So the aim of the SVM is to, among all the possible linear hyperplanes that we can build, to define the one that maximizes the margin, what is called the margin among between both classes. And these 2 points here are called the supervectors, where the margin lies. But this is in the case where the points can be easily separated by a linear classifier. But what happens in the nonlinear case, that is in the case where we can see that here we can separate these two classes from with a classifier, but not with a linear one, but with a non-linear, like in this case. Well, here SVM also works. How? Well, what it does is to translate the original data from the original space where they belong to through a high-dimensional space via what is called a feature map. And in this high-dimensional space, the data become linear and can therefore be easily separated with this linear classifier. So mathematically, this can be formulated as this optimization problem, where in the objective function we basically want to maximize the margin, and this term here is a regularization term that allows some misclassified points to have some misclassified points, and this constraint here essentially states that each point should be correctly labeled. So in the previous two examples, so the red points should be all of them in the right part, and the left points and the blue points, sorry, in the left part. And in the case where the data are nonlinear, we just simply apply this feature map, as I told you before. But the problem is that this feature map is usually unknown. So it is normal to use not the primal formulation, but the dual formulation, where here it's not necessary to know the explicit expression of phi, but the dot product between the phi of two different points. And this dot product is known as kernel function. Recall that at the beginning of the presentation, I have told you that we want to select features, or we want to select the most important bases or the most important nodes. So the point here is that we want to have not linear classifiers like this one, but like these ones, where here we know that the first demand is the most important one to classify these two set of points. So let's see how we formulate this problem. To do this, we use the well-known anisotropic Gaussian kernel, where here we have a bandwidth value gamma j, which express the importance given to each one of the features. So the larger the gamma, the larger the gamma, the most role, the most the relevance that this feature has. But we have to take care, because we know that if all gamma j are zero, then all points are classified in the same class, and we don't know this. And also, if gamma j tend to infinity, then we will have overfitting. So it seems that it should have a kind of trade-off between the model complexity and the classification accuracy. And this is exactly what we model in this optimization problem, this min-max approach, where we have well, what at first sight it can be a bit ugly, but it can be easily decomposed in two parts. The first one is devoted to the model complexity, and it is expressed in terms of the gamma, the norm of the gamma vector, and the second part is devoted to the classification accuracy, and it is expressed in terms of the SVM, the dual formulation of the SVM problem. And this C2 and 1 minus C2 parameters model the way that we balance each of the two objectives that we have in this objective, in this function. So which are the advantages of our approach? Well, we have proposed a model that simultaneously select features and classify, contrary to those methods we just select features but do not take into account that classifier that we are using. Contrary to those methods that needs to know a priori the number of features that should be selected, our method that doesn't need that, because the number of selected features is directly provided by the method. And since we have a strong duality, we can reformulate the problem to its single level equivalent reformulation and solve it using off-the-shelf solvers where just two parameters are tuned via cross-validation. And if you want to know more info about this model, I suggest you to visit the ResearchGate where this preprint is. Yes, to know a little bit more about the preprint that is currently under review. But so far, I have just told you about a pure data-driven method. But at the beginning of the talk, I told you that we want to use not only the information coming from the from the data, but also from the physics of the problem. So how can we incorporate this information to the model? So this min-max approach is a non-convex optimization problem whose local optimal solutions are strongly dependent on the initial solution that we used. So we say, okay, why don't we incorporate a physically and data-aware initial solution that take into account both things, so that take into account data and physics of the problem. And this is exactly what we do, and this is exactly what I'm going to show you in this illustrative example, where we run the min-max approach for 3 different initial solutions, one pure data aware, one pure physically aware, and the third one that combines physically and data information. And we will see how are the difference between the classifiers that we obtain. So in this illustrative example, we have a 3-node system where we have generation and demand in nodes 1 and 2. We have no generation, no demand in node 3, and we focus on the congestion status of the second line. So we don't care about line 1 or line 3. We have run the unit commitment problem, and these are the kind of data that we obtain. So here, the blue points are denotes the demand points at which the second line is not congested, and the red points, the demand points, where the second line is congested. So here we have used a pure data aware initial solution that is 0.1, 0.1, and here we don't have any information about the interpretability. So here we are just stating that both features play the same role. And so we can say that this initial solution is not so good because apart of not giving us interpretability, it has some errors here, some classification errors. So it's seen that it's not so good. Then the second initial solution is a pure physically aware initial solution that gives us interpretability, because here it says that the second feature is the more important one. But we can see that they yield 2 errors because the classification doesn't fit the training data. And I forgot to say, sorry, that this initial solution comes from the PTDF, the PTDF values of the system. And then the third initial solution is a physically and data-aware initial solution when we take into account the physics of the problem and the data. So how we take into account the physics? Well, we know that there exists an inherent explicit expression, a explicit linear expression between the flow and the demand. So we say, okay, we know that this physical rule exists, so we are going to and they are related with the PTDF, so we are going to take into account that. But instead of using the coefficients given by the PTDF, we are going to use the coefficients given by a simple regression rule. And these are the coefficients of the regression. And here we say that this is the best solution among the 3 that we have already used, because it says that we have that the second feature is the most important one, but we have also to take into account the first feature. And also, even though we have here some misclassified points, the classification performance is better than in the previous two initial solutions. And finally, just conclusions, we have designed a mathematical optimization approach, which is modeled by means of a min-max optimization problem where we select features to identify the status of the lines. And we have included the physical and data information via initial solutions, and the illustrative example shows promising results. And as a future research line, we are going to see how this is scaled to a bigger study with hundreds or thousands of lines and nodes, and how affects the possible relationships, such as the correlation among features, to the classifiers. These are some of the references that we have used, and that's all. Thank you very much for your attention.